I'm going to talk about ROC2 graded coefficients of C2 Eilenberg-MacLane spectra. So this is going to be a talk about computations. And the computational talks sometimes have the problem that at some point there is a sentence which sounds like, well, let's look at the 143rd page of the spectral sequence, and then everybody's out. So instead, I will try to sweep the technical details under the carpet, and I will try to convey the idea how these computations should be performed and what would be the good good method of performing these computations. So let's start with a quick overview of the problem. It is somehow a trivial statement that, well, it is a trivial statement that in the non-equivariant topology, computing the singular homology of a point with coefficients in some abelian group or some ring R is very simple because we just look at the dimension axiom, and we see that it is concentrated in degree 0, and well, it is 0 everywhere else. So just one remark, if you have any questions, please feel free to interrupt. And the problem is that it's not so easy in the equivariant world. To see that we can compare the homology of a point, on the left-hand side, we have just singular homology with coefficients in F2, and it is concentrated in degree 0, no surprise. But on the right-hand side, we have coefficients of a point, we have a homology of a point with coefficients in the equivariant analog of F2, which is a constant Mackey factor on F2. And what we can see here is that this homology is graded over a ring of representations. I will make sense of this a little bit later. And over this line of trivial representations, we can see the similar pattern as in the classical non-equivariant homology, but it is no longer true when we leave the comfortable world of trivial representations. So the goal of this talk would be to describe a method for the computations of the C2 equivariant homology of a point, a method which will have two properties. It will make these computations feasible, and also it will allow us to unveil as much structure as possible. So our object of the study will be C2 equivariant ordinary homology of a point, but rather we are going to compute the coefficients, ROC2 graded coefficients of C2 Eilenberg-MacLane spectra. And as we will see later, these spectra, Eilenberg-MacLane spectra C2 equivariant, are just representing objects for ordinary equivariant homology. And the method which we are going to use will be the Tate method as developed by Greenlees and May. So this is a method which will be based on the Tate diagram. So firstly, let's start with a small overview of what Braddon homology is. And instead of giving a definition here, I will just give a couple of properties or how we should think about this homology. So let G be a finite group. And Braddon homology is, first of all, the ordinary equivariant homology theory, which means that it satisfies equivariant versions of Eilenberg-Steenrod axioms, together with the dimension axiom. Also, it takes Mackey functors as coefficients, and it is graded over the ring of G representations ROG. And what do we mean by this ring? So small aside, what is ROG? How we define it? So we start with ROG twiddle, which is a semi-ring, the semi-ring of isomorphism classes of real G representations with the direct product taken as sum and the tensor product taken as product. And ROG is defined as the Grothendieck construction on ROG twiddle, which just means that we add additive inverses. And for example, the ring of representations of the cyclic group of order P is this polynomial ring divided by the polynomial x to the power P minus 1. And in particular, ROC2, the ring of representations of cyclic group of order 2 is two-dimensional in a sense that it is generated by the class of trivial representation denoted by 1 and the class of the sign representation denoted by sigma. Okay. So coming back to the Breton homology, it is represented by the equivariant Eilenberg-MacLane spectra HM. And these spectra are defined by the property that their Z-graded homotopy groups, G-equivariant homotopy groups, are concentrated in degree 0. So that's similar to the non-equivariant case. And the value is given by the value of the Mackey factor on the level G. However, of course, it is not anymore true when we are passing to the gradation over whole ring of representation. And how are equivariant Eilenberg-MacLane spectra and their homotopy groups connected with Breton homology? So by this formula here, the homotopy groups of G-equivariant homotopy groups of HM are the same thing as G-equivariant ROG-graded Breton homology of a point with coefficients in M. So here, by the 5-pointed star, we mean that these homotopy groups or homology are ROG-graded, which means that the Vth homotopy group is the space of G-equivariant classes, homotopy classes of maps from the representation sphere associated to V. So this is compactification, 1-point compactification of V to HM. So our goal would be to compute these homotopy groups. So G-equivariant homotopy groups of Eilenberg-MacLane spectra are ROG-graded, which we'll denote as here. And we will do it over cyclic group of order 2. Also, we will refer to these homotopy groups as coefficients and coefficients of HM. And I hope this won't be misleading because the word coefficients will be very often used in this talk. So since these are going to be our main object of study, let's say something about C2 Mackey factors. So I'm pretty sure most of you already know this stuff, but C2 Mackey factors, let me just say that they have particularly simple structure, because C2 Mackey factor is just given by two abelian groups, one on the C2 level and one on the E level, where the abelian group on the bottom level may have possibly non-trivial action of C2. And these abelian groups are connected by two C2 equivariant maps, the transfer and the restriction. And these maps are connected by the formula, which is the Mackey condition in this case, which means that if we go through the transfer and then we go down by the restriction, then it is the same as multiplying by the element 1 plus gamma, where gamma is the generator of C2. And some examples of C2 Mackey factors are the constant Mackey factor on Z. So here on the bottom level, we have the integers with the trivial action of C2. On the top level, we have again integers also with the trivial action. The transfer is given by the multiplication by 2, and the restriction is given by the identity. A similar example is the constant Mackey factor on F2. So on the bottom level here, we have F2, of course, with trivial C2 action, because we cannot have other action of C2 on F2. On the top level, we have also F2. The transfer is given by multiplication by 2, but since we are in the characteristic 2, this is just 0, and the identity is given, the restriction is given by the identity. The crucial example for us today will be the Bernstein-Mackey factor, which is given yet again by integers with trivial C2 action on the bottom level, and this ring on the top level, and I gave it somehow the computational form, but really this is just the Bernstein ring of C2, and omega is a class of C2 mod E in the Bernstein ring. Okay. And I think it's mistake here because probably the transfer should be multiplication by omega here. Yes.
I think your identity should be omega squared is equal to 2 times omega, actually. The thing you are dividing out. Omega squared
minus
is not, omega squared minus 2 omega is 0. That's what I remember. If omega is the free guy, right? For you.
Yeah, that's true. Sorry.
Yeah, and then then I think it's then I think transfer is just multiplication by this.
By omega, because then the restriction is just sending omega to 2, so that's fine now.
Yeah.
Okay. So the transfer is given by the multiplication by omega, and then the restriction is given by identity on the class of 1, and by sending omega to 2. And yet another example, so this will be an example of a Mackey factor which has a non-trivial action on the E level. So this will be the fixed points Mackey factor of Z twiddle. So here Z twiddle means integers with the action given by the sign. So this Mackey factor is given by Z twiddle on the bottom level and 0 on the top level, and the restriction and transfer are obvious here. So the coefficients of Eilenberg-MacLane spectra over C2 may be thought of as having 3 levels of structure. So first level is an ROC2 graded abelian group. But also by the fact that every Mackey factor is a module over the Bernstein-Mackey factor, the coefficients of every Eilenberg-MacLane spectrum carries a structure of a module over coefficients of the Eilenberg-MacLane spectrum associated to the Bernstein-Mackey factor. And thirdly, if our Mackey factor is actually a green factor, which means that it is a ring Mackey factor with respect to the box product, then the coefficients of HM have also the structure of ROC2 graded ring. So let's say a couple of words about motivation. Why do we care? So first motivation, at least in my taste, it's strange and interesting that computing homology of a point is hard. And point is the simplest non-empty topological space, so it is good to know its homology. But I should probably give some better motivations for this. So the coefficients of Eilenberg-MacLane spectra are fundamental in computations of ROG-graded homology or cohomology of other G spaces, well, G spectra or other objects. So for example, yesterday we saw a homology of a point, CT equivalent, ROC2 graded homology of a point with coefficients in F2 constant Mackey factor. We saw it yesterday in Prasid's talk a couple of times. And also the Eilenberg-MacLane spectra are basic objects in the category of G spectra. So we better know and understand their homotopy for other computations. So for example, I'm not sure if you can see the, okay, so Zoom is somehow cutting the very bottom of the slide. So I will just read it for you because I don't really know how to fix it. So the other computations here, for example, the other famous method of computations in the equivalent homotopy theory is the slice spectral sequence. And there, Eilenberg-MacLane spectra and shifts of Eilenberg-MacLane spectra appears as -1 slices and 0 slices. So also we better know its homotopy if we want to run the slice spectral sequence. So now a little bit of history of computations over C2. So the first instance is legendary unpublished work of Stonk. And well, because it is unpublished, we cannot really see it, but everybody in the field is referring to this work, so I'm giving it here as well. And based on this work, Lewis in 1988 computed the coefficients ROC2 graded, of course, of Bernstein-Mackey factor. Then the most general answer was given by Fairland in 1999 in his PhD thesis, and these results were reiterated in Fairland-Lewis paper from 2004, where they gave an ROC2 graded abelian group structure of the coefficients of arbitrary Mackey factor, and also a module structure over coefficients of the Bernstein-Mackey factor. Other explicit computations were given by Caruso in 1999. I'm not sure who was the first, whether it was Caruso or Fairland, so I'm just giving it in this order. So he computed the coefficients of IGF2, and Dagger in 2005 computed the coefficients of IGZ. So one might ask, what is the point of this talk if the coefficients of Eilenberg-MacLane spectra are already computed? So we are going to reprove Fairland's result using other methods, and we are going to extend these results a little bit by saying something about, well, actually by determining the multiplicative structure of coefficients of Eilenberg-MacLane spectra associated to green factors. And also the secret goal of this talk is to advertise the method based on the Tate diagram as a good method to doing such computations. So before we go to actual content of this talk and the Tate method, let's sort out the easy part first. So the easy part of the coefficients is the part graded over multiples of the sign representation. So let A be the element of the minus sigma C2 equivalent homotopy groups of a sphere spectrum, given by the inclusion S0, S0 to S sigma. And This element is also known as the Euler class. And having this element, the multiplication by A on the coefficients of Eilenberg-MacLane spectra may be described as follows, that multiplication by A is a monomorphism if x minus 1 is y. It is an epimorphism if x is equal to minus y, and it is an isomorphism otherwise. And from this description, really the message is that it is an isomorphism unless it leaves or hits the antidiagonal. And in all of the coefficients of all pictures which I will show you today, we will see the kind of pattern of vertical periodicity, and this is exactly given by multiplication by A. This periodicity is broken exactly at the antidiagonal. May be broken. So in particular, using this multiplication, we can get that the groups, that the coefficients groups, well, entries at the multiples of the sign representation are given by the kernel of the restriction in our Mackey factor if we are over 0, above 0, the co-kernel of the transfer if we are below 0, and the C2 level of our Mackey factor if we are at 0. And how we prove it, we use the cofiber sequence. C2 plus goes to S naught goes to S sigma. And we use the fact that applying that smashing with HM or taking C2 homotopy classes to HM and applying these factors to this cofiber sequence exhibits them transfer or and restriction in our Mackey factor. So on the left, we have just a reminder how our Mackey factor looks like. And by the vertical axis, I will always denote here the multiples of the sign representation. And so when we are on this y-axis, then if we are below 0, we are the values are the co-kernel of the transfer. If we are above 0, the values are the kernel of the restriction. And if we are at 0, we have our C2 level of the Mackey factor. So this was the easy part. So now let's proceed to harder part. Strange. Okay, so now let's say a couple of words about the Tate square. So for now, let G be a compact Lie group, and let EG be the free contractible G space. And we define a cofiber sequence known as the isotropy separation sequence as follows. We just send EG plus to S naught by sending base point to base point and the rest of EG plus to the other point of S0. And a homotopy cofiber of this will be denoted by EG twiddle. So now let X be a G spectrum. And there is a map which will denote by epsilon, sending X to the function spectrum from EG plus to X. So the rest of the sentence is cut somehow by zoom, but this map is induced by the first map in the isotropy separation sequence. So now by smashing epsilon with the isotropy separation sequence, we obtain the following diagram. So here we have X smashed with the isotropy separation sequence. Here we have F, e.g. plus to X smashed with the isotropy separation sequence, and they are connected by respective smashes. And there's a fact that this map, the left-hand side map here, is a G equivalence, and this is due to the fact that epsilon is a non-equivalent equivalence, and thus after smashing with EG plus, it becomes a G equivalence. So since the left-hand side here is an equivalence, we know that the right-hand side square is a homotopy pullback. So now we will name the entries in this diagram. So let X subscript H be EG plus smashed X, smashed with X. So this is known as the free G spectrum associated to X. X superscript H will be the function spectrum from EG plus to X, and this is known as the Borel completion of X. X superscript phi will denote EG twiddle smashed with X, and this is known as the singular G spectrum associated to X. And finally, X superscript T will denote EG twiddle smashed with FEG plus to X, or EG twiddle smashed with the Borel completion, and this is known as the Tate spectrum of X. So after renaming the entries, we get the following diagram. So this is what is known as the Tate diagram. There is some delay. Okay. And in particular, the right square in this diagram is known as the Tate square. This square has the property of being, as we said before, homotopy pullback, and also it has additional feature that if X is a ring G spectrum, then the Tate square is a homotopy pullback of ring G spectra, in the sense that all of the entries of the Tate square are ring G spectra, and this square is a homotopy pullback. And this is also true for R modules. So if X is a module over some ring spectrum R, then the Tate square is a homotopy pullback of R modules. So now let's take a look on the strategy, how we are going to proceed with the calculations. So let M be an arbitrary C2 Mackey functor. And here we have just a reminder how the Tate diagram looks like. So we start with computing. Our first step will be to compute these two entries. And so the coefficients of the Borel completion and the coefficients of the free C2 spectrum. And this we'll do by respectively homotopy fixed points and homotopy orbit spectral sequences. Next, we will derive from the bottom cofiber sequence the coefficients of the Tate spectrum, or alternatively, we can just invert the class A in the coefficients of the Borel completion. And this is due to the fact that the Tate spectrum is defined as EC twiddle smashed with the Borel completion. And EC twiddle has a very nice model as infinity sigma. So this is a representation sphere of infinite sum of copies of sign representation. And since S infinity sigma is given as colimit of smaller representation spheres, we have that coefficients of the Tate spectrum are the isomorphic actually to the colimit of consecutive multiplication by A. Therefore, they're isomorphic to the coefficients of the Borel completion with A inverted. So in the third step, we will infer the coefficients of the singular C2 spectrum by the following lemma. So suppose that X is a C2 spectrum which is non-equivalently connective. Then if this map between categorical fixed points from XC2 to the C2 fixed points of its Borel completion is a connective cover, then so is map from X phi the fixed points of the singular spectrum to the fixed points of the Tate spectrum. And finally, we will compute the coefficients of our starting Eilenberg-MacLane spectrum. So let's take a look. How does it look like on diagram? Oh, no, sorry. Firstly, I need to give very important references. And the references for this method are Grindis and May book, Generalized State Cohomology. And also this particular method, this strategy was used by John in the paper 4 Approaches to Cohomology Theories with Reality, where he computed the coefficients of IHZ and also of the K theory with reality. Okay. And now we can see how this strategy looks like on a diagram. So our first step will be to compute the coefficients of these two guys. Then in step 2, we will infer the coefficients of the Tate spectrum. Step 3 will be to compute the coefficients of the singular spectrum, and the grand finale will be the coefficients of the spectrum which we wanted to compute. And note here that it may seem that there is a lot of happening on every step, but every step in this procedure is actually easy, it is manageable. And this approach is kind of algorithmic. It works always for every Eilenberg-MacLane spectrum. So let's proceed to the step 1 and let's discuss the spectral sequences which will appear in the step 1. So recall the definitions of the free spectrum associated to HM to be EC2 plus matched with HM, and the Borel completion is given by this functional spectrum. And the space EC2 plus has a very convenient model given by the unit sphere in the infinite sum of copies of sigma. And this space as infinity sigma has a filtration by Skeleta given as here. So these are just smaller unit sphere. This is unit sphere in the sign representation in 2 times sign representation and so on and so forth. And thus, consequently, we obtain a filtration on the free EC2 spectrum and the Borel completion. And the spectral sequences associated to these filtrations take the following form. So here, the first spectral sequence takes as, so this is homotopy orbits. Well, both spectral sequences take on the second page as entry. As entry is the homology and group homology and cohomology of C2 with values in non-equivariant coefficients of HM. So here is what I mean by this. These are just homotopy groups of the restriction of HM thought of as C2 modules. And these spectral sequences converges to what we want them to converge. So the first one, known as the homotopy orbit spectral sequence, converges to the coefficients, Z-graded coefficients of the free spectrum. And the second one, which is homotopy fixed point spectral sequence, converges to the coefficients of the Borel completion. But actually, we want these spectral sequences to be tree-graded to compute not only the Z-graded coefficients of the spectra, but arrow C2-graded coefficients of the spectra. So for this, we use the small trick that the coefficients x in the spot x plus y sigma of the Borel completion, well, so this is just the definition of these coefficients. But by some classical adjunctions, we see that it is the same as the maps from S x to this function, to the categorical fixed points of this function spectrum. And I will rewrite what is written at the bottom level. So this is just pi x of f s y sigma h m h c2. And using this, we can define our homotopy. This is homotopy fixed point spectral sequence to be tree-graded. So the third gradation is the gradation over twisted degrees. So this is where it appears. And it really means that for every value of y, we have separate spectral sequences. So differentials always live on the sheets connected to different values of y. The tree gradation actually appears if we wanted to talk about multiplicative structure of this spectral sequence. So yet again, it takes S entries group cohomology of C2 with values, with coefficients in just classical singular homology of the cubed homology of SY sigma with coefficients in the bottom level of our Mackey functor. And C2 action on this abelian group is given by action of SY sigma and on SY sigma and on the entry of the Mackey functor. So as we expected, this spectral sequence compute what we want. So it computes RC2 graded coefficients of the Borel completion. And by the similar argument, we can get the tree-graded homotopy orbit spectral sequence as given here. So now let's see how these calculations work on some toy case. So our toy case will be an example which I gave at the beginning. So the coefficients of IHF2, well, F2 is the constant Mackey functor on F2. So again, here we have these three graded spectral sequences, and we use them to compute these coefficients. However, for this particular Mackey functor, the coefficients appearing in this group cohomology and homology coefficients of this group homology and cohomology become very simple because this just become F2. And group homology of C2 with coefficients in F2 is very simple and well understood. So we can easily compute that the coefficients of the Borel completion and of the free spectrum are given as here. So just to recall, these are multiples of the trivial representations, and these are multiples of the sign representation. And here we can see the copies, the shifted copies of group cohomology and group homology appearing along the rows in these pictures. So now we will derive the coefficients of the Tate spectrum. So we can do it by in a twofold way. So first, you can derive it from the bottom level of from the bottom row of the Tate diagram. And then what we will see is actually Tate cohomology of C2 with coefficients in F2 along the rows. And this is actually where the name of the Tate spectrum comes from, because the Tate spectrum is what represents Tate cohomology and generalizes somehow Tate cohomology. And other method which we can use is that we can take the coefficients of the border completion and invert A. So what we see here, maybe I will write it, A, multiplication by A is going just one step down by sigma. And what I have not written in this presentation is that these coefficients are actually aperiodic, which means that in the Tate spectrum, in the coefficients of the Tate spectrum and coefficients of the singular spectrum, you'll always see that everything along the columns is always isomorphic. So in particular, for the Tate spectrum and for the singular spectrum, we just need to compute either anti-diagonal or the bit graded over trivial representations. So by the connective cover lemma, this is our step 3, we compute the coefficients of the singular C2 spectrum. So these are just the same as the coefficients of the Tate spectrum, but after cutting everything below with the fixed degree below 0. Okay, so we have computed all of the entries of the Tate diagram. And so now the final step would be to derive the coefficients of our spectrum HF2 using this diagram. And here I have to admit that I'm not sure if this square is pullback of anything, but we don't really need it because just by the fact that here we have exact rows, and by chasing on the diagram degree-wise, we can get, as expected, that the coefficient of HF2 looks as follows. So this was our toy case, and the general answer, so the answer for general Mackey functor is a little bit more complicated. So this is, as I said, result of Fairland, which I reproved using the Tate method, that the arrow C2 graded coefficients of general of Eilenberg-McCain spectra associated to general Mackey functor looks as on this picture. And I know that a lot in here, but here on the y-axis we have functor. Here we have a couple of submodules and subquotients of the E level of our Mackey functor, and these are bits which somehow depend on the group homology and cohomology of C2 with values in the E level of our Mackey functor. And in particular, we see that these coefficients depend only on the structure of the Mackey functor. This is, of course, not very surprising because they don't have anything else to depend on, but we should also describe how they are depend. So this is how they are depend. So this is general answer for the arrow C2 graded abelian group structure. So another example are the coefficients of the Burnside Mackey functor. So here again, I will 2 omega here. So here we see a little bit different patterns. For example, in the 4th quadrant, this homology is concentrated in even fixed degrees. So the columns corresponding to x equal 1, 3, and so on and so forth are always 0. Again, the column corresponding to -1 is also 0. And we have non-trivial entries above 0 on the y-axis. And also we see 3 different groups appearing over here. So the Burnside ring, Z, and F2. And actually, using the Tate square, or by different methods, but I did it by the Tate square. We can describe the ROC2 graded ring structure of the coefficients of the Bernstein-Mackey factor. So it is fully determined by the following. It is strictly commutative in the sense that if we have a graded ring, we have that xy is equal to yx up to some sign. But in this case, we have that these are actually equal. There is no sign appearing here. And we have two elements which will describe as this structure in full. Well, three elements because the other will be class omega. So the element A is the element over here. It is element of degree minus sigma. Degree of A is equal to minus sigma. And here what we see, multiplying by A is responsible for this kind of vertical periodicity. This periodicity breaks on the antidiagonal. And also what is general pattern for these coefficients is that if we are on the right half plane, these coefficients are always 0 above the antidiagonal, and on the left half plane, the coefficients are 0 below the antidiagonal, and this is also action of A responsible for it. And the second element which will describe this structure is the element U. So this is an element of degree 2 minus 2 sigma. And this is an element responsible for this kind of antidiagonal periodicity. And how we can describe this multiplication. So multiplication starting at the degree 2 sigma minus 2 and finishing in 0 is the transfer in the Bernstein-Mackey factor, and the multiplication by U starting at 0 spot is the restriction in our Mackey factor. And finally, there is one more bit which we need to describe. So I need to rewrite it. So if tau is a generator of H of the sigma spot, so we are right now over here, and we can show that this class is generated by omega minus 2, sorry, this entry is generated by omega minus 2 times A to the power minus 1. So this gives us a full description of the ROC2 graded ring structure of the coefficients of the Bernstein-Mackey factor. So let's say something about multiplicative structure for general green factor. So just to recall that a green factor is a ring Mackey factor with respect to the box product. And if M is a green factor, that its coefficients are an ROC2 graded ring. And again, using the Tate diagram, we can actually describe its structure. And ingredients of its structure, of this structure, are given as follows. So first degree, oh, there's some delay. Okay, can you hear me? Okay, very good.
Yes.
So, okay, I just had some delay here, so I was just unsure. So ingredients of this multiplicative structure are firstly the action of the ring, the coefficients of the Bernstein-Mackey factor. And as we said, this ring is described by 3 elements, so we will describe the action of these 3 elements on general Eilenberg-MacLane spectrum. So action of A is easy to describe by using the fiber sequence. We did it at the beginning. Action of U, and this is a small theorem, is that it can be described in terms of structural maps of the Mackey factor. So This is a heuristic statement, and of course cannot be called a full theorem. But it's just that there are something like 7 or 8 cases how this map, how U acts, depending on where the multiplication starts. So, for example, we've seen in the Bernstein-Mackey factor that if the multiplication by U hits a 0 spot, then it is a transfer, and if it leaves the 0 spot, then it is restriction. And the third ingredient is the action of omega, the element of the Bernstein ring. So this is what reflects the graded commutativity in ROC2 graded rings, since if we have elements of the coefficients of this Eilenberg-MacLane spectra, and this is true for at least for all coefficients of general C2 spectra, then xy is equal to yx up to sign, where the sign is given by -1 to the power 8 times a prime, and 1 minus omega. So this is kind of non-trivial sign coming from the action of the Bernstein ring to the power b times b prime. However, we can prove that for all Eilenberg-MacLane spectra, this sign is trivial. So for any green factor m, the ring, the coefficients of this green factor are actually strictly commutative, which means that the sign coming from the graded commutativity rule, this one is always trivial. So the second ingredient are 4 elements which we also need to describe. So these are elements of degrees 1 minus sigma, sigma minus 1, 3 minus 3 sigma, and 3 sigma minus 3. However, the relations with A and U may be derived from the Tate square and as an example, we have here again IHF2, and here we have the non-trivial class of degree 1 minus sigma, but from the fact that IHC2 and star here, sorry, no H here, C2, and here we have, so this is mapped from the coefficients of IHF2 to the coefficients of its Borel completion. We can derive that lambda squared is equal to U. So kind of corollary of all of this stuff is that ROC2 graded ring structure is determined by these ingredients. In other words, it is always, this ring is always strict commutative. It is described, determined by the action of the coefficients of Bernstein-Mackey factor and elements of degrees 1 minus sigma, sigma minus 1, 3 minus 3 sigma, and 3 sigma minus 3. But these elements actually probably may also be described in terms of A and U. So another example, so this is somehow weird example, is a norm of F2. So let B be this norm of F2. So this is a Mackey factor which looks like this. It has Z mod 2 on the bottom level and Z mod 4 on the top level. And here what we can see is, well, here we have action of A. So this is already what we know. Here we have U, but here we have non-trivial class of 3 minus 3 sigma. And how it's connected to element U. So here we have kind of virtual class lambda. We have no entry at 1 minus 1 sigma, but if we take a ring map from the coefficients of this spectrum to the coefficients of its Borel completion, which appears to be also Borel completion of IHF2, then we see that there is an element lambda. And thus we can see that there is kind of virtual lambda, which has the property that lambda squared is equal to U. So in other words, we have that lambda, that the square of the element of order 3 minus 3 sigma is the same as the cube of the element of degree 2 minus 2 sigma. And also, just a remark that this Mackey factor has also the property that it has the only non-zero columns are in fixed degree 1 and minus 1. Okay, so I have 2 minutes left, or maybe a little bit more because I started with small delay. So let me say a couple of words about future directions with these computations. Actually, this will be a future direction because there is only one direction which I can think of. So the Tate method may be iterated. And for example, let's see how this iteration works over C4. Let's start with X, a C4 spectrum. So here we have the Tate diagram, and assume that we want, again, to compute C4 coefficients of X. So the bottom level is, again, sorted. We have spectral sequences, so hopefully we will be able to compute them. And then by the properties of the Tate spectrum, this will be probably manageable. But there is a hard bit, which is computing the coefficients of the singular spectrum. But here, over C4, we can use a trick, the following trick. So let's let Q be equal to the quotient of C4 by C2, which occurs to be isomorphic to C2. And then you can use the fact that categorical fixed points, C4 fixed points of the singular spectrum are actually Qth fixed points of the C2 geometric fixed points of X. And so now we need to, rather than computing C4 coefficients of some spectrum, we just need to compute C2 coefficients of this spectrum over here. And for this, we can run again the Tate diagram. So the aim of this would be to compute coefficients of IHM for C4 and possibly for groups of cyclic order of being the powers of 2. And just to mention, well, I need to mention that over C4, these groups for Eilenberg-MacLane spectra were computed, sorry, not this one, for the constant Mackey factor by Min-Kong Zheng. And I think he actually used this kind of iterated Tate method. And by Nick Georgakopoulos, sorry. So he computed the coefficients of the Eilenberg-MacLane spectrum associated to the constant Mackey factor on F2. And I think that would be all what I wanted to say. So thank you very much for your attention.
Un homme de son âge et de sa force n'avait rien à redouter de la mort.
Thank you. Can you hear me now?
Yes, I can hear you.
Okay, that's, I don't know if you want to hear me, but are there any questions or comments?
So Irakli had a question.
I had a simple question. Yeah. So
go ahead.
Yeah, thanks for the talk. I mean, I enjoyed it. Nice computations. So, but what I'm wondering about, what's the reason not to try C3, for example, or any other cyclic group of prime order? These are already computed, or?
I mean,
Louis did some computations a lot.
Yes. So sorry, I should mention this, that actually computations for Ferland by Ferland and Lewis were for cyclic group of prime order, and there is no reason for not doing it.
You could redo it again with these methods, that too.
Yeah, so this was just that up to now I focused on C2. So also the hope somehow would be to use this method for, as I said, C4 and other cyclic groups of the order being powers of 2. But this is possible because this groups have kind of linear order of subgroups. So for example, using this method for computations over the Klein group, Klein 4 group might not be so simple.
But what about other prime powers? That's also should work the same, like C9 or something. I mean, these methods, the methods you were describing does sound like you just using its prime powers or prime orders. I mean,
yes, and the fact that C2 has only two subgroups, one the full one and one the trivial one.
Yes, CP does as well, but of course, representation theory becomes trickier, right?
So yeah, that might be a problem, and also group cohomology and homology is just a little bit more complicated. Yeah, a little bit, of course. It is well understood, but in this particular case, it was very simple.
Mm-hmm. Okay, thank you.
Any other questions or comments? Then we can just thank Igor again for the nice talk.
Thank you.